Has more recent stuff. I'm not bordering on research, so usually will give the first half hour will present some research results, I guess, and then Xiaowei one.
And there's some break between.
Sorry.
The break between two. My one and Xiaowei.
There will be just a brief break.
Oh, okay.
We need to
Okay. Yeah, sure. Okay. So maybe, yeah, it should be a bit more rough in this talk. So what I want to talk is essentially the modular Therapeutic surfaces. But it gives an idea as this, for what I wrote as K modular as Gromov-Hausdorff compactification, which is of very differential geometric origin, and maybe it's quite well-known thing. So the theorem is we can more or less compactify modular Therapeutic surfaces or smooth Therapeutic surfaces by k-stable object. So suppose this is moduli, which is quasi-projectivity of smooth Therapeutic surface, or Therapeutic surface of degree d. And degree here means minus kx square. This is positive because minus kx is supposed to be ample. And yeah, let's say this is theorem B because the earlier theorem was A. And we can, at least abstractly, as a metric space, we can cook up topological space. Gromov-Hausdorff compactification. So as Claude explained, so once okay, for simplicity, so our argument gives more, but for simplicity of the argument, we suppose something which had been known for a long time. So this condition is equivalent to that this modular is not point. So if the modular is point, there's nothing to think. We cannot compactify point by adding some. So let me see. So these things are known to Wittgenstein. Due to Tian in 80, so 90 or around that. And consider the Gromov-Hausdorff limit of those things, which is a compact metric space with which is a limit of K-Einstein Therapeutic surfaces. And so this is K-Einstein Therapeutic. And smooth Therapeutic. And it's their Gromov-Hausdorff limit. And well, this is a priori just compact metric space, but it's known that this is actually Therapeutic obifold. So this is quite rather surprising thing. Therapeutic obifold. I think in this two-dimensional case, it's Theorem.
Some others. Anderson.
Anderson? Okay. And okay. So this is also true for higher dimension as well, which is quite big result due to Donaldson and Son. For any dimension, this is true. So what I mean by Q-Fan variety is a log-terminal projective variety with log-terminal singularity. And in two-dimensional case, log-terminal singularity is nothing but orbifold singularity. So that's Therapeutic orbifold. So we have quite algebraic geometric structure on that. By using, we get this kind of algebraic geometric limit by using differential geometric point of view. We can cook up this topological compactification at least. And on the other hand, so what the theorem says is we have some explicit algebraic geometric compactification. Geometric compactification. Very precisely speaking, this is a compact algebraic space. Compact and compact and separated compact and separated algebraic space. More Shetson analytic space. And what we have is, so like Attrich says theoretically, we have this inclusion. And what we have is, and of course we have topology here by Euclidean topology. And this is, we have Homeo. So that corresponding limits correspond. So we have grow mass hyperbola limit, and as this is algebraic geometric compactification. So on the boundary, there's some log-derivative surfaces put so that the limits correspond. Makes sense.
And this is for smooth advances?
Yeah, compactifying smooth derivative. So the modular is like on the boundary, we have derivative orbifolds, which is, K-Einstein as well. So we have K-Einstein orbifold.
Like orbifolds of that degree.
Right. Yeah. So general picture is like this, so smooth. K fan is inside, right here. So the general dimensions picture is like this, and we expect this is exists as a this kind of modular compactification. Modular of K-Einstein things. K-Einstein Q-Fan as a projective variety, but we stick to this case in this talk. Let me also mention that in higher dimension case, this Zariski open part is already exists. But that is the K-Einstein funnel with smooth funnel with automorphism finite. And the problem is how to compactify as a projective variety.
Do you have a description of the peso, the degenerations of the peso? They are understood.
Sorry?
I mean, do you understand the degeneration of the peso? I mean, there is a description of the.
Yeah. So this is these are explicit, and I will give explicit description for now. To see bit of feeling about that. So the construction is MAG. Well, I would say this is the definition of MAG. So as I said, this if this is bigger than 4, this is trivial. So if these 4, oh, this is actually due to Mabuchi Mukai, which is was quite pioneering in this direction. So we consider, I think this was in even in late 80s. So even before K-stability, they were thinking like this. So consider smooth Therapeutic of degree 4 as an intersection of 2 quadratic in P4. Then these things are parameterized by Grassmannian of this space. So each member gives the vanishing locus as quadratic, and if you have 2, then we get intersection. So and so consider so take GIT quotient of this with respect to the natural action of SL5, because just rotating inside P4 doesn't change the surface itself. We just rotate inside P4. So consider GIT quotient of this one. Then that is what we want. Of that is so say this is H, then H over SL5. So this is MAG. And so we are parameterizing some GIT polystable member. So this is corresponding to, every point of this one is some intersection of 2 quadrics, sometimes singular. But anyway, these are all GIT polystable things. And so when I started, 20 or something.
15 minutes.
15 minutes, okay. So maybe D equals 3 density is easier. So I just write as usual MAG is just a usual GIT moduli of cubic surface. And D equal to, this is a bit technical. And so what we do is we regard the general member as smooth member as a double cover of P2 along quadratic. So each member corresponds to some quadratic. So we can consider a GIT quotient of, take GIT quotient of SL3. I'll take GIT quotient PH0 P2O4 divided by SS3. And let me write this M prime. Then, as this is every point is corresponding some polystable quadratic, this looks like a natural thing to think. But actually, this is not the right thing to think because this has a this includes some this could include double conic part. So which I write as P.
Worse things than that, right? Probably 4 times a line or something.
It's unstable. Yeah.
Okay.
Yeah. And what we do is blow up this point. So I think I will write this. Or, well. So what I just wanted to show is the simple GIT construction of the simple way of taking GIT quotient is not enough in general. So AG is a blow up of P2, a blow up of this M prime at this point, and this exception divisor is parameterizing a double cover of P114 along degree I don't quite remember. What is it? Oh, Sony is on here. 12 or something. Yeah, wrong. Well, let's see. Yeah, degree 8, I guess. Curves. And this is matching with this original description of M prime because this was a double cover of P2, and this can degenerate to double cover of P114 because P2 degenerates to P114. And this matches. And we precisely formulate what is this modular in terms of stack. And then we construct a coarse moduli of that as this guy. And okay, anyway, so what we do is very, in a sense, the idea is quite simple. Proof. So the first is this M. We show this is actually set theoretically. Just consider as a set. This K-Einstein smooth derivatives and those derivative surfaces. Then we will show that we show that this is a subset of this MAG. So that is all smooth members, and all those Gromov-Haus limits should be something parameterized in this case. this moduli. Then supposed to show a set. Then automatically this gives a homomorphism. So let me. At least I should. So the first part is more crucial. The second part is, roughly speaking, due to the reason that this is compact. We know that because we are attaching all Gromov-Hausdorff limits, and then on the other hand, this is Hausdorff as it follows from the construction. So this is a Hausdorff algebraic space. At least we know that this is projective variety for d not equal 1. So I think I didn't mention, but the d equal 1, this is very complicated. Okay, but this might be new compactification. Obviously, the construction is motivated, designed to get this inclusion, so that we can see this. And the first. Okay, yeah, that's it. Thanks. So the first part is okay. So first of all, so this Gromov-Hausdorff limit. So it's derivative or before that. And this is K-Einstein. So this is due to Theorem. And then, so there are many restrictions. So one is, actually this is also, there's also a restriction on the singularity. Q-Gorenstein smoothability. This is roughly speaking that this O before this self is first smoothable, and also this canonical divisor continuously smooths out. So I cannot define how, but I can just say that this is the definition is the total space of the definition. Deformation is has Q-Gorentz Q-Cartier canonical divisor. So anyway, and also we have a Bishop Gromov inequality. So once we have a orbital singularity, this should be like that. I don't know. So once we have a singularity, then we apply a well-known inequality of monotonicity of the ratio of this cutted volume, and the same thing for sphere. And then, finally, as this is diameter finite, we get a volume and the volume of the top whole thing, which is just kx. And this degree, and then we have also the volume of sphere here. Then what we get is anyway. So if P is look like C2 over gamma, then what we get is kx is degree times this one is less than 12. And so, for example, like if this is degree 4, then this means gamma is 0/2, which is quite restricted because we can only get A1 singularity. And then we can apply a classification of log derivative surface. Because the singularities which can appear is quite restricted. One reason is this one reason is, and we can basically classify the singularities up here, and we get the index of the derivative, and we use a classification so that what kind of thing limit can appear, can be seen in that way. And finally, we use K-stability.
Group, Picard rank 1?
No, not necessarily. Derivative before. And well, very roughly speaking, this K-stability, we use kind of technique. So in general, to relate K-stability with classical GIT stability, it's hard. But if the parameter space has Picard rank 1, for example, like hypersurface case, it's easy to see that K-stable thing parameterized in that parameter space should be GIT stable in that parameter space. So, like in the hypersurface case. Yeah, and we can apply Hilbert manifold criterion in this setting, each setting. For example, like degree 3 case is hypersurface, so we can directly apply this. And also for degree 2, can be well, at least as far as Gorenstein part, we can regard as a double cover, well, as like a cortex moduli, so which is hypersurface. So we can apply similar thing, and then we get more restriction. So there are many restrictions anyway. So Gromov-Hausdorff limits should be okay. Oh, I think that's the end.
Okay. Maybe just a question or something, and then. So I mean, I just had a question here. I mean, it seems to me that you are already overdetermined, or not.
Sorry.
I mean, it seems to me that, I mean, like, so in the end, what you want to prove is like a Gromov-Hausdorff limit is a semi-stable del pet. So it seems to me that you already have lots of restrictions from the beginning, and I'm wondering, like, the last condition, is it really used, or?
Yeah, these are used. So.
Okay.
So what? Yeah. So what we are saying is Gromov-Hausdorff limit should satisfy many things.
Mm.
And what we did is we corrected these things and cooked up a moduli.
I see, and those are exactly the GIT stable stuff.
Right, because we basically used GIT.
Okay.
It's like locally GIT matched together.
In some way, this construction relies a lot on the fact that you know a priori what the algebraic geometry module is going to be. Right? So you want to do this in, say, higher dimensions.
Yeah, in higher dimension, it's.
But
Yeah.
the Gromov-Hausdorff part still works.
Yeah, right. Yeah, they prove. Yeah.
Okay, so I think we should stop here. We'll take a break just to erase the blackboard.
So sorry, shall we? Talk too much?